So it's 6 p.m. I will wait for a couple of minutes and see if people join. Otherwise, I will start after 3 4 minutes. So it's already 6:05. I will start the session now. So let me introduce myself first. I am Ananya, a PhD scholar in the Department of Electrical Engineering, IIT Kanpur. Share my screen. Okay. Okay. I've just started the session. I will have not start like I have just given my introduction. So if you are new, then I am Ananya. I am a PhD scholar in the Department of Electrical Engineering, IIT Kanpur, and my specialization is microelectronics and VLSI. I work in semiconductor devices lab here in IIT Kanpur, and I will be your TA for the session. I'm not sure if you have attended earlier sessions or not. I conduct these sessions on every Tuesday between 6 from 6 to 8. Okay, so these live sessions are mainly for problem solving sessions. So in this course, sciences and actuators, we don't have like that many numerical problems, but we take some like theoretical questions in these sessions, and also I discuss the topics those were covered in this week, so that everyone is in the same page. Ideally, you should watch all the videos, lecture videos and lab classes before coming to this session. Okay, so welcome to this live session for the course Sensors and Actuators, and this is week 7. So I hope you can hear me clearly. Okay, I'll stop this um, floating mode of Google Meet. It's difficult to like write, so I will be in the presentation mode most of the time. If you have any doubt, you can unmute yourself or write in the chat box. I will check in the like as we go through the session. Okay. Okay, so let's start the session. So I always start with a brief overview of the topics those were covered in this week. So the first topic was so in this week we discussed about the professor discussed about the physical vapor deposition techniques. We have already discussed about different physical vapor deposition techniques in earlier weeks as well. So we mainly discussed about E-beam like thermal evaporation, and this week E-beam evaporation and sputtering was discussed. So we have I think we have taken few questions on sputtering and thermal evaporation earlier. So this will be just a brush up of your knowledge. So first we will discuss about E-beam evaporation. So as I discussed earlier weeks, we have like physical vapor depositions are mainly two types. We do either evaporation, so we melt the material, we evaporate it and then deposit on our substrate, or we can do sputtering, like we remove the material by sputtering, okay, from the target, and then we deposit on the substrate. Now in evaporation we have two configuration or two type of system: E-beam evaporation and thermal evaporation. So what is a thermal evaporation? So basically the diagram for a E-beam system and thermal evaporation system looks similar with few differences, and the working mechanism is also quite similar. So we basically evaporate a material, we melt the material, the target material. Say we want to deposit aluminium on our substrate to make some interdigitated electrode or some other metal, then we use this deposition techniques. Basically we evaporate the material and then deposit. But the difference with thermal evaporation and difference between thermal evaporation and E-beam evaporation is that how we melt the material. Okay, in thermal evaporation, as the name suggests, we thermally we heat the material until it reaches the melting point, and then the evaporation happens. So how it is done? So inside the thermal evaporation system, we take a basket or a boat. So boat can be of this kind of shape. Okay, you will place your material here, and then you two electrodes will be connected at these two ends, and we pass a current that will generate heat due to the Joule heating. As you know that when a current is passed through a resistive material, heat is generated because of Joule heating, and that Joule heating will actually melt this material, and that will lead to evaporation of this material, right? In instead of a boat we can use a basket also. So basket will be like this spiral kind of thing. Okay, you will place your material in between these spirals, and then you will apply current to this basket or to this basically wire, and that will lead to resistive heating or joule heating that will melt your material, and that will cause evaporation. Now, and the problem with thermal evaporation is that it's a very simple system, very easy to implement, the instrumentation wise the cost is also less. But the problem here is that we uh, this is based on resistive heating, so we apply a current. So the problem is that we cannot evaporate a material which has a very high melting point, because we need, then we need a material that can actually hold this target material that you want to deposit, and we have to pass a very high current through this boat or basket, whatever you are using. And for that we use e-beam evaporation. So this is the diagram of an e-beam evaporator system. So this is the basic diagram. The arrangement can be different little bit depending on the system. So how it works, so there is this filament. So we apply a very high current to it, and because of that electrons will emit. So this is based on thermionic emission of electrons, and then because these are electrons, an electron beam is generated, and this electron beam we can deflect it using some kind of lens. Now what kind of lens? So you know that light can be deflected or directed by using an optical lens. Now what kind of lens can actually direct or deflect electron beam? That is, we can use electromagnetic waves. Okay, so you know that how electric and magnetic field affects the movement of electrons. So you can see here there is this magnetic field. Basically you can call this kind of a lens electromagnetic lens that directs the electron beam towards the source. Now here you can see this is kind of a board or a crucible that holds our source material, the material that we want to deposit. So this can be of material, say graphite. So in the system we have in our lab, we use graphite crucible to hold our material, and then we place our material here, and this electron beam actually locally hit this source. So we try to direct this electron beam say in the middle of our source. We don't want to heat our crucible, uh, we mainly want to melt our source, and then this beam actually scans little bit. So if I can give you a top view of this, say this is your material and this is the crucible, this is your target material. So electron beam will move in this kind of a direction, so that it does not hit at the same spot. Also it does not heat the crucible, it only heats the target material that you want to evaporate. Now because of this high energy electron beams, so this material, even if it has a high melting point, that will melt and then it will evaporate and then deposit at the substrate that we keep at the top. Okay, and here you can see there is this rotation. We kind of rotate this substrate holder, we call it a substrate holder, wafer is our substrate. We rotate it so that we get a uniform deposition. Now there is this another component, shutter. So say you want to deposit a very thin layer, say you want to deposit a 50 nanometer of your target material, say you want to deposit a 50 nanometer of nickel layer on top of your wafer. So you will control like your deposition rate such that the deposition rate is kind of slow, because if the deposition rate is very high, even if you close the shutter, your thickness will vary significantly. So you will maintain your deposition rate like a very slow deposition rate, and then you will close the shutter, or at times like when you know that the thickness you already achieved as like 50 nanometer, if that is your target. You don't want your thickness to vary like in a very large range. So you don't want, say, 50 plus minus 5 nanometer is okay, but you don't want your film thickness to be of 70-80 nanometer. In that case, using a shutter, you can actually like get a film that is of your desired thickness. Now again, you have to be careful with the deposition rate. If the deposition rate is very fast, even if you close the shutter, so there will be like a little bit of extra deposition during that time also, that will also change your film thickness. Okay. And another component here you can see is the vacuum pump. So we before starting dust deposition, we actually create vacuum inside the chamber. This is to there are a few different purposes I have discussed earlier in case of thermal evaporation as well. So why we need a vacuum system to why we need a vacuum inside the chamber? So this is for so that no contamination happen. We don't want any kind of other material on our film or on our target. And also the reason is that you can see here, when the materials evaporate, it generally like follows this straight line path. So if there is another particle, if there is no vacuum or the vacuum is less, so if there are some particles, then your atoms will hit. So it will come out from your source, and it will collide with the particles inside the chamber and will go to a different direction and say will sit at the chamber walls. Okay, so we don't want this kind of thing to happen. That is why we initially maintain a very high vacuum also, and during evaporation also we monitor the chamber pressure, so that it does not get very high. So we want a very slow and steady deposition. So we don't want pressure inside the chamber to become too high. Okay, so we do this deposition at low pressure itself, whereas in case of sputtering, when we do the deposition, it is generally at a higher pressure. Initially like the pressure will be low, and then we do the deposition at a higher pressure. But in case of evaporation, we try to do it at a lower pressure, so that we get a very uniform deposition, and atoms are moving in a straight line path and depositing only at the wafer. Okay, and so that we can control our thickness very precisely. Okay. And another component here, inside this evaporator, you can see this crystal monitor. So this deposition monitor actually determines the it checks the thickness. Okay, so as I mentioned you that, say you want a thickness of 50 nanometer, then how you will know that you are actually getting 50 nanometers? So that information is given by this crystal monitor. So so it will display, so this will be connected to a display system where you will see what is the expected thickness of your film. So you can see here the monitor is placed like this. Some amount of material will also go, like evaporate and sit in the crystal monitor also. So each time depending on the like atoms those are deposited on the crystal monitor, that will tell you the thickness, what is the expected thickness. The thickness may vary a little bit, because you can see the monitor is normally placed like here, your wafer will be at a different place, but it will not be that different. Okay, and if like you can determine this factor, like how, what is the factor, by which factor actually the thickness shown by the crystal monitor and actual thickness vary. So you know how to measure the thickness of a film on wafer. So we have studied about profilometry technique and other kind of technique, like how to determine reflection data based thickness measurement techniques that we have discussed. So first few deposition, what you can do, like you can measure the thickness experimentally, and then you can compare with the thickness that is shown by the crystal monitor, and then you can find the factor that Okay, say if the crystal monitor shows this 100 nanometer, we are actually getting a thickness of 110 nanometer. So you know the factor, and then you can use that factor to determine, like, to stop your deposition. uh, you can use the shutter so that you get some desired thickness from the next time onwards. Okay, so this is about the different components in a thermal evaporator system. So it is very similar, EVM evaporator system. It is very similar to the thermal evaporator. Only difference is the source by which we are actually melting our target material. Okay, and there are certain advantages and disadvantages of EVM evaporation compared to thermal evaporation. So I'll write down few. You already know this thing. This is just for your reference. So I will give you a comparison. First, thermal evaporator and e-beam evaporation. So it uses resistive heating, okay, to evaporate the material. And it uses electron beam, so which is of high energy to heat and evaporate material. Okay, so this is the basic difference. And then the advantages of thermal evaporator is that it's a very simple system, so the cost is less compared to thermal evaporation. Okay. And another advantage is that it can be easily used for different metals. So you know that aluminium, it has a melting point around, like, if I remember correctly, around 660 degrees Celsius. And the board we normally use, or the basket we use, that is of tungsten or molybdenum, those have a melting point above 3000 degrees Celsius. I don't remember the exact number. So we can use this thermal evaporation system for a, like a range of metals. Okay, it is uh, it is we can melt those material easily using this kind of boat of tungsten or molybdenum. And those are the materials we normally use. So if you want to make an electrode, so you don't need to go for other kind of system. If you don't care much about the like quality and other things, you just need some metal, then thermal evaporation can do it very easily. Now, compared to this, the advantages of EVM evaporation is it can melt high materials with higher melting point. Okay. That is the advantage, and the disadvantages are so for thermal evaporation it will be kind of opposite. Whatever the advantage and of EVM evaporation, that will be the disadvantage of thermal evaporation. So we have limited material option, and another disadvantage is that here you can see in case of thermal evaporator, so we pass the current through this boat or basket. Okay, so it actually heat up the boat or basket. So even though that the melting point difference is like very high for the target material and the boat material, but there can be some contamination. Okay, so some material, some atoms from the boat also will be present in your like evaporated material, and that can also affect your film quality. Whereas when you want a very good quality film and you don't want any contamination, here you can see the electron beam is kind of very focused, and we are focused only on the target material, not on the crucible. So the contamination will be less for EVM evaporation compared to thermal evaporation. Okay, so if you want a very good quality film, then you can go for thermal evaporation. The disadvantages of EVM evaporation is that it is more complex and expensive. There is this filament and this electromagnetic lenses to direct the electron beam, and then you scan this electron beam in the target material. So all this arrangement is extra compared to thermal evaporation. That includes cost. Also, in case of EVM evaporation, you need a very good cooling system because the generated heat will be very high, like even though it is locally, the heat will be very high. So, uh, there should be a cooling mechanism so that it does not affect or break down any parts of your like inside the chamber. Okay, so these are the difference and comparison between thermal evaporation and EVM evaporation. As I mentioned you that the boat material in case of thermal evaporation or EVM evaporation. So in our lab in EVM evaporation we use graphite crucible. So that has again around more than 3000 degrees Celsius melting point. In case of thermal evaporation we use, now it can be different in different lab, different system. So we used tungsten to basket, so that is again have like very high melting point, I, if I remember correctly, around 3400 degrees Celsius. So these values are very high. But when you do evaporation, you should also consider few other things. Say if you are doing this evaporation using this kind of a basket and you are keeping your material here. If your material, say for example, if you want to deposit nickel, nickel has very high density, so some material will actually fall down instead of going up. So when you want to evaporate a material, the vapor pressure of this material is also important, because if it has higher vapor pressure, then only it will go up and sit on your wafer or substrate. So choosing a material for e-beam evaporation or thermal evaporation is not just based on the melting point. So you should also consider what boat you are using, what kind of crucible you are using, whether you are using a boat or a basket. Okay, but in case of like most metal, thermal evaporation works. If you want good quality films, you can go for e-beam evaporation. So depends on your application, what kind of film you want, and also depends on what is available with you. I hope this is clear. If there is any question, you can ask. Next topic is sputtering. So few people have left the meeting, they may join again. I'll just continue. Next topic is sputtering. So sputtering is another deposition technique. So what what sputtering means? It means ejecting material from the target, and target is our source, and the material will sit on the substrate. So this is the block diagram of a sputtering system. So this is our sputtering target. So this is the target, and then what is the process? We introduce a sputtering gas, usually argon, and then we apply bias to this sputtering target, so in between target and this substrate, and so that because of this biasing, this sputtering gas argon will get ionized, and there will be a creation of plasma. So argon plus an electron, so you know what is a plasma. So this argon plus ions will hit the target, and some materials will get ejected from the target, and that will sit at the like substrate here. Okay, substrate or the wafer that you are using here. So the definition of sputtering is: sputtering involves, okay, let me remove this. I think it is difficult to see that. My screen is visible, right? Okay. Yes. Next is sputtering. So sputtering involves ejecting material or atoms from target, which is our source, onto the substrate. So for sputtering, we normally use argon or any other suitable like inert gas. That is because we don't want any contamination in our target or in our film. That is why we use argon, and also the reason is that we want to eject materials or atoms from the target. So we want a material, we want an inert gas that has an atomic weight close to the target that we are using, target material. In most cases argon works, and if it is a very light material, then neon is used as a sputtering gas, and if it is a very heavy element, then we use krypton or xenon as the sputtering gas. Okay, so I'll write it here. For sputtering light element, we use neon as sputtering gas. And for sputtering heavier element, we prefer krypton or xenon. Okay, this is because we want the sputtering gas and the target material have similar atomic weight. Okay, now there can be different types of arrangement in a sputtering system. So a sputtering can be of DC type, or It can be of pulse DC, it can be of RS sputtering. So that is the energy that you are providing to create the plasma, that is different for all these cases. Okay, so this is a very basic diagram of a sputtering system. Now it can be magnetron sputtering as well. So there can be some magnets placed here. Okay. So what does magnets do? These magnets basically redirects this argon ions. So you can see these are argon plus and these are magnets. So again, electrons are affected by magnetic field. So these ions will actually concentrate and will concentrate here, and the argon ion will again come back to the substrate, again heat the not substrate, again come back to the target and again heat the target, and so the same uh, argon ions present, that will actually hit the target multiple times, and that basically increases the deposition rate. So this kind of different arrangements are used, but the basic mechanism is that we have a sputtering gas, we create plasma, that plasma hits the target and that ejects the material from the target, and that sits at the substrate. Now let me show you, like I have given you this diagram for an EV evaporator. A thermal evaporator is very similar. Now this is the diagram of a sputtering system. We have this kind of system in our lab. So here you can see, so this is the substrate holder. Okay, you will place your substrates here, and this is your target. Okay, in this system there may be multiple targets. So this is your target. Okay. You will place your targets here. Now the size of the target will depend on your system. So it can be a 4-inch target and 6-inch, 2-inch target. So the system we have, like this ATS 500, so it has place for 4-inch and 2-inch target. So you'll have this target, you will place it. So these are the electrodes here, and there will be magnets here because it's a magnetron sputtering system. And then we create so this is the main chamber, and we create vacuum using some kind of a vacuum pumping system. Okay, this is the this is for this is the control unit where you will like press the button and do some operation. Okay, this is called a load lock system. So we don't open this main chamber directly unless it is required. We want to change our target or some problem is happening in our system. So what we do normally, we place our samples or substrates here, and there is a magnetic arm here, like there is a movable arm here, and we press this button, and this arm actually transfers this our substrate to this substrate, this position, this holding position. Okay, we don't open directly this chamber because we don't want any contamination inside our chamber, like any contamination in our target. Or if we directly open this chamber, then it will directly see the environment. So after we close it down, when we want to pump down the system, we create vacuum, then it will take a very long duration. Okay, that is why we use this kind of a load lock system. And we first create vacuum here, and then we transfer this our substrate here instead of directly opening it. Is there any question? Okay. So it is not compulsory to put the substrate, but you can see here. So this is the arrangement is like this, but you can see here. So these are this connections, right? So this part, suppose, see, I don't know how to answer your question directly, but I have seen all the systems having configuration like this. Instead of putting your substrate, ideally it should be possible, like if you you can bias your target at, at the top also. But you can see this arrangement, this whole arrangement is like very heavy. You have this magnets, it's not that the weight is high actually. When there is some problem happens, so we once we try to open this whole system, but it's actually difficult. And the connections are here below. So this portion, we have the connections. If there is some problem, we try to check here, we open this and check the connections here. So it is easier to, I think, put the substrate holder here, and then you can see like the atoms will eject like this. In case of thermal evaporation also, you can see the substrate holder is put at the top, and then it travels, so it travels in this straight line direction, it sits at the substrate. So I think even though the in case of sputtering, the atoms does not move in a straight line, um, like in case of this thermal evaporation or EV evaporation. But I'm actually not very sure how the movement of atoms happen, but maybe that is also important. That is why the configuration is kept like that always. I have never seen a configuration where the substrate holder is kept below. So I'm sorry if I cannot answer your question exactly, but these are the things I think that is why the configuration is kept like this. The systems are kept like this, at least the ones that I have seen. I will search if that kind of configuration is there. Like, see, what you want, your argon atom should hit your target atom, right? So this is argon plus, so you bias it in a negative way here. Okay, then only your argon atoms will come here and hit. So I also don't use the term anode and cathode that much. Just remember this, that these are argon plus ions and that should hit our target. So that is how we will do the biasing. If it is positive, then positive, that will not happen, right? The sputtering will not happen. Just remember that. So this plasma will be argon plus and electrons, a combination of all these things. So basically it's argon plus ion. Okay, I hope it is clear. Okay, so this is a sputtering system. These are the main components. The load log, this is the main chamber, this is the interface where you this is like the control unit, and you will have your pump. So this is the rotary pump connected to the load log, and there will be another pump, because rotary pump cannot create very high vacuum. There will be another pump like turbo pump uh, that will create high vacuum inside the chamber. Now there are certain disadvantages and advantages of sputtering. So we have discussed about different physical vapor deposition techniques, evaporation, like in evaporation again, thermal evaporation and e-beam evaporation, and as well as sputtering. Now there is, all these things are for deposition of thin film, but the process are a little bit different, and there are certain advantages and disadvantages of each processes. Now in case of sputtering, so you can see here, we can actually have a large area target, and we can do the deposition on a large substrates. Okay, this, as I mentioned here, the targets are of size of around say 4 inch in diameter, I mean. So these are big targets, and you can do deposition. You can go for like longer deposition time and get a very thick substrate. Whereas in case of EVM evaporation or thermal evaporation, you will not place that like uh, the you don't have, you can get this kind of thick film, and you cannot get very uniform film, because these normally moves in a straight line path, and your uniformity will not be that good in case of evaporation. That is what I feel like. Okay, so for large area and uniform deposition, sputtering is preferred. And then and we can go for sputtering of different materials, different kind of alloy. Like we can make we can use reactive sputtering also. Say we are depositing certain material, we have a target of certain material, and then we also introduce, along with the argon gas, that is the sputtering gas, we can also introduce other gas, say like oxygen, so that we get a oxide of that material. So we can play around those things also. We can this will just need another gas line connection, and then we can introduce this process is called co-sputtering or reactive sputtering. We can play around with the composition very easily. Now you know that there are different types of material like indium tin oxide, azo. All these materials can be sputtered. Like we can get a film using sputtering technique. So these are like different compounds and alloy materials. These are possible with sputtering, not uh, like it's difficult with other deposition techniques. And also another advantage is that in case of sputtering, so sputtering is not very directional. So if you have this kind of a step on your wafer, say you have already done some lithography and you have this kind of a step. So if you deposit a film using evaporation, then because in evaporation the materials move in a straight line, so your coverage, film coverage at these portions will be less. So you will get a good film here, but not here. So in case of sputtering, because it's not directional, you will get kind of like a uniform film on top of your structured film. Okay, so that is another advantage. If you need that, then that is helpful. Now another advantage is that, so these advantages I'm just explaining from the slide that was shown in the lecture videos. So one point was that sputtering, it cleans the substrate, it cleans the target material for deposition. So this So what we do during sputtering, we do something called pre-sputtering. So in our targets, at the top layer maybe of say some material, there may be oxide formation. Say you want to do a copper deposition, many times the copper target will have an oxide layer, very thin oxide layer, and you don't want to deposit that on your substrate. So without so there will be two kind of shutter here in this kind of system. One is at the top of your target, and one is at the top of your substrate. So say you create your plasma, and actually the sputtering is happening, but you are keeping your shutter closed, both the shutters. Then your material, the top layer of your target, will be sputtered, like on the shutter, on the side walls, or anywhere, but not directly on your substrate. So we normally do this process for like say 20-25 minutes, and after that we actually open the shutter to get the actual deposition on our substrate. So that is why we can get a good quality film using sputtering. There are certain disadvantages as well. Because we use ion bombardment, like a sputtering gas, that can sometimes damage our substrate, damage our target material as well. So that is one disadvantage of sputtering. And then in case of sputtering, so we normally need uh, like a bigger target. Okay, it's 4 inch or 2 inch. So getting a target can be expensive because you will need a lot of material, whereas in case of thermal evaporation or EV evaporation, if you want to do, say, thin deposition of gold layer, so that will not cost much, like material wise, compared to sputtering, because there you initially itself you need a bigger target material. Okay, so these are some of the advantages and disadvantages of sputtering. So I'll write down few. So large target, so uniform deposition over large area. It can provide good step coverage. I'm comparing with evaporation. If there is any non-uniformity in your structure, that will in your wafer or substrate, that will actually cover, like sputtering will cover those things. Pre-sputtering, that will help remove any contamination of the target. And some disadvantages: rate of deposition, for some material, example SiO2, can be low. Okay. But then there is one advantage of sputtering, that it is not like it happens in one go. So we have a big target. If we can create, like, control our plasma, if our plasma is not fluctuating, even our deposition rate is very slow, very less, then also we can go for like longer deposition time and get the desired thickness. Okay, so yes, SiO2 deposition, it's actually very slow. We have an SiO2 target here, but if we go for deposition for longer duration, this problem can also be overcome. Okay. Now, the deposition we do in case of sputtering, this is relatively at higher pressure. As soon as we introduce argon gas, the pressure, chamber pressure actually increases. So, there is a possibility that there is some impurities, and that will actually contaminate our film. Okay. If our argon gas is not like pure, that will also create problem. Like, if a small amount of oxygen is also present in the, like, argon cylinder, that will also change our film property. Basically, there will be some oxygen, some oxides in our film. Okay, this is what we faced in like once in our lab. The argon was not very pure. Okay. Now, what process you will actually use, what kind of deposition techniques, whether evaporation or sputtering, that depends on what you are aiming for. Say, if you want a good step coverage, then you will go for sputtering. If you want to go for larger area, then you will go for sputtering. If you want to deposit your metal and you want a directional deposition, then you go for evaporation. Okay. And one thing also you should remember this, that in case of evaporation, the you are heating the material, whether it is for thermal evaporation or e-beam evaporation. So even though there is a distance between your source and wafer, there will be some heat that reaches your wafer. So this is a practical problem that I'm telling you. Say, if you do your if you are doing your deposition at a very high temperature, that is what usually necessary in case of thermal and e-beam evaporation. Then say you already have like a pattern film, you have the substrate and you are having some photoresist layer on top of it, and you are keeping this for your deposition. Okay, after that you will go for etching and then you will remove the photoresist layer. Say, now this heat will actually affect your photoresist layer. Okay, so you should be careful while doing metal deposition after lithography, like with photoresist layer. That can create some problem. Sometimes it's difficult to remove the photoresist easily, like it does not get removed very easily, because at high temperature some cross linking, some chemical reaction that happens, and that actually changes the output will not be the desired that you think. Okay, I hope there are people in the meeting. And okay, so let's quickly go to the next few slides, then I will start the questions. So another topic, so these were mainly the lab classes, so I will not explain much, because the lab videos, lab classes are self-explanatory. So in one class this peristatic pump was described. So it has this kind of a flexible tube, and fluid moves from one end to the other end. You know, these are rollers, and it basically presses the liquid, and that basically that's how we get a continuous flow of fluid through using this pump. Okay, so the applications are in microfluidic devices. Those were discussed in the class itself. I will not go into the details. Next is the oxygen plasma system. So it has different uses. Like say we use it for surface cleaning. Okay, because in an oxygen plasma system we'll create a plasma that will contains like oxygen ions, and these high energy ions will hit our surface, the wafer surface, and that basically cleans the surface. And we often use to remove photoresist layer as well. So say it if you are not sure if your photoresist layer is removed correctly, like completely or not, then you can just keep it inside the oxygen plasma system, and that will actually remove any residue on top of your surface. Okay, and sometimes this is done to create like increase adhesion or bonding as well. Next, it is also used for surface activation and bonding. Okay, the example is PDMS with glass that was shown in the class. So basically what it does, the oxygen plasma, there will be some ions in the plasma that will actually create some dangling bonds on top of our surface substrates, and when we press it with each other, that the bond, there will be formation of some kind of covalent bond, and that basically bind up the two substrates. Okay, so you can see like what kind of bonding happens between PDMS and glass due to oxygen plasma system. And what are the basic components in the oxygen plasma system? It has a chamber. We will have a chamber, and we will have a vacuum pump. Initially, we will create vacuum so that we can get a stable plasma. There will be an oxygen cylinder. Okay, so we will provide the oxygen cylinder, and there will be an RF coil and RF generator. So we need RF energy, radio frequency energy, to actually ionize or create the plasma. So it's normally around 15, I don't remember the exact number. So you use a certain kind of RF frequency, RF energy to create the plasma. We apply this energy to uh, to the like oxygen environment that is inside the chamber, and that creates the plasma. So it has these components: a chamber, a oxygen cylinder, and then a RF energy system that will create the plasma. Okay, this is a very simple system. It has variety or like multiple applications in fabrication lab. Okay, next, there was this demonstration of IR based sensor using Arduino. So we had discussed like how to interface sensor with Arduino earlier. There are few lab videos as well in earlier weeks, so I'll not go into the details again because the interfacing is kind of similar. So you will have some output of your sensor that will you will take depending on whether it is an analog output or a digital output, that you will connect it to the digital or analog pin of Arduino. Okay, and then you will read the data, and based on that you will provide some output from the Arduino to some actuator. Say in this case, you are making this sensor for you are using IR sensor for the security purpose. So you are keeping your sensor. So we know that our body radiates infrared wave, right? Any like non anybody with a non-zero temperature, that will radiate some heat wave, and that is basically infrared radiation. An IR sensor can detect the presence of human being because of that. And say if someone is present, and you can write a code like if the output of the IR sensor is high, say if it is detecting some human being, some alarm will blow, like a buzzer will blow, something like that. So this is a very simple security system. So we used to make this kind of circuit in our BTech. So you will find many YouTube videos and tutorials how to make this kind of circuits as well. Next topic was microfluidic devices for biochips with PEMS molding. So we had learned about how we can make like micro channels in PDMS. So what we do, first we have a kind of a master that is of silicon. We make the master with standard photolithography processes. Then what we do, we have the structure. We actually have the inverted structure what we actually want on the master, and then say we have our master like this. This is our master. This can be of silicon. Okay, we make this using standard photolithography. Then what we do, we pour PDMS and we do the curing. Okay. and then we peel off this PDMS layer, we will get the microchannels. So that will have opposite nature of the master. Then we bond this PDMS with glass to make our channels. Okay, this we have already discussed, and the lab video shows how it is done. Okay, uh, so let me go to the questions next. Is there any question or doubt, or I will start the questions? Okay, I will start the questions then. Okay, if you have any question, then you can ask. You can unmute also instead of writing. Yeah.
Ma'am,
Yes.
can you repeat that first slide, that E beam and thermal once again?
Okay.
Can you explain?
Okay, I'll just briefly explain. So, I have discussed about thermal evaporation earlier. So, how it is done? We have like a boat like this or a basket. Okay, so this is a boat, usually of tungsten or molybdenum. So this basket we normally use in our lab is of tungsten, and boat sometimes molybdenum. We apply current here, and because of this current there will be some heating due to Joule heating, because we are applying electric current that will generate heat. So this heat will actually melt the material, target material. Say we are keeping aluminium here, and once it get melts, that will evaporate and sit at the wafer at the top. Okay, similar kind of arrangement is there in case of e-beam evaporation, uh, but the difference is that instead of this heating arrangement, we have a filament that will we apply this high voltage, and that will basically emit electron, this filament, because of thermionic emission. You can see what thermionic emission is. Now electrons will be ejected. This will be of high energy. The electrons will be of high energy that can like create heat. Now we want to direct this electron beam to our source. This is our target material. Say we are keeping nickel here. Now how we will deflect this our electron beam to our target or source? So we will use magnetic field. You know that electrons will be affected by electromagnetic wave. So these are kind of like lens. So what we do, we have lens to guide optical like light, right? You know what a lens does. uh, these are kind of lens that actually guides electron beam, but these are actually magnetic field. So these are electromagnetic lenses to guide electron beam, and electron beam will hit the source. And what we do, we don't we want this electron beam to hit the source or our target, and we kind of do a raster scan. We don't want to hit only at one spot. We move this electron beam like this kind of an arrangement. So this is called raster scanning. We don't want this electron beam to fall at our crucible. So this is our crucible. This is usually of, can be of graphite, any other material, again that should have like a very high melting point. We don't want this electron beam to fall on the crucible. So we try to keep it inside our target material, and this material will then, because of this energy, this will heat up, and then it will evaporate and will sit at the wafer. Now the other components are this is the quartz crystal monitor. So this actually tell you what is the thickness of your deposition. Okay, this will be connected to a display unit that will give you the number, that is the expected thickness after the deposition. Now, how it actually works, I will explain later in one question also. I can explain like briefly. So it has a crystal monitor that oscillates at a certain frequency, certain resonance frequency, and that resonance frequency will change again if there is some deposition because of the weight. So due to some deposition, the weight of this monitor will change, and that the frequency will change, and that will basically give you after like some internal calculation, that will give you the expected thickness. Now we have this shutter as well here. Say you want to deposit a 50 nanometer of nickel film, then you can see like if your monitor is showing the value, your desired value, then you can close the shutter and you will stop your deposition. Okay. And another component here is the vacuum pump. We want to create vacuum here. That's I explained earlier when I discussed about thermal evaporation as well. We don't want any contamination because of any particle, and also we don't want any particle inside the chamber during deposition as well, because so materials will be evaporated from the source or the target, and if there is some other material, that will hit and deflect the material, and it will get deposited on the chamber walls or somewhere else. Okay, we don't want that. That's why we keep a high vacuum during deposition in case of thermal and EVM evaporation. Whereas in case of sputtering, we don't do the deposition at a very high pressure. Initially we maintain a very high pressure so that everything was taken out and like it's very clean inside the chamber, and then we do the deposition at a higher pressure. But for e-beam evaporation and thermal evaporation, we do the deposition itself at a very like high vacuum or low pressure environment. Okay. And these are the advantages and disadvantages of thermal and EVM evaporation. I will share the slide. You can go through it, and if there is any question, you can ask later as well. I hope this explanation is clear. And one more thing, if you are interested in learning like about thin film deposition, then you can. So I have this book. I will give you the name. So this is not like for this course particularly, this is not for sensors and actuators, but if you are interested in learning the portion of thin film and other techniques, then you can go through this book, Material Science of thin films. This is by Milton Ori. Okay. Again, this book is not for this course. If you are interested in learning how the thin film deposition and how those things works, then you can maybe go through a few chapters of this book. Okay, I hope it is clear. You can confirm me in the chat box, and then I will proceed. Okay. So I will write down the first question. What is a key advantage of sputtering over evaporation? So evaporation can be thermal or it can be evaporation as well. So both the techniques are similar. Option A is higher deposition rate. Option B is better step coverage and adhesion. Option C is lower cost. D is works with metals. What is the answer? I will wait for some time so that you can tell me the answer in the chat box. So, what is the answer? Option A. Option A is higher deposition rate. So this is the advantage of sputtering. Okay, so I will explain. Option A is not the correct answer. Option B is the correct answer. So answer is B. Better step coverage. And adhesion. So this is the main advantage of sputtering. So as I mentioned earlier, here you can see that if we have a conformal structure like this, so what happens in evaporation? Evaporation happens in a straight line, on a straight path. Okay, so the coverage here, so the deposition at these walls will be less in case of evaporation. But sputtering is not directional. It can be an advantage. Okay, when we want a good step coverage, so if we have a structure like a very conformal kind of structure, we'll get a good deposition using sputtering. Also this happens at like when high energy atoms will hit our substrate, because these are ejected material due to sputtering. So the adhesion between the film and the substrate will be better compared to evaporation. So this is the main advantage. Now higher deposition rate, now deposition rate for certain material in for sputtering is actually less compared to evaporation. And lower cost, it's that is also not true. Like thermal evaporation system is a fairly simple system. We just need some heating resistive element. Now again the overall cost will depend on how sophisticated the instrument is, and depending on the vendor, the manufacturer. But in general, sputtering will need some kind of like RF energy source system. There will be magnetrons, so that actually includes more cost compared to a simple like thermal evaporation system. Works with metal? No, sputtering works with a variety of material. It can be used for insulator like silicon dioxide as well, and we can make like alloys and compounds using sputtering. Okay, I have discussed about coarse sputtering or reactive sputtering. We can make like oxide. We can introduce another gas during sputtering process that will actually create some other material on our wafer, like the position of some other material on the wafer or substrate. Okay, so metals, thermal evaporation is usually good for metals. Okay, so I'll write down it. In evaporation, atoms travel in a straight line path. And may not cover complex structure. Whereas sputtering provides better step coverage. Sputtering also leads to stronger adhesion as high energy atoms impact the substrate with more force. Okay, so I hope it is clear. I will go to the next question. Let me keep this in this mind. So this is a true or false question. In E-beam evaporation, the high energy electron beam can potentially damage the sensitive substrate. Whether this statement is true or false, and you can give me the reason as well why you think this is true or false. I'm waiting for a minute or so that you can answer. think this is true. We don't hit our substrate with E beam and like electron beam, uh, but there is a possibility that it can damage the substrate as well. Okay. We hit our target with electron beam, not our substrate. You can see here, but still there can be some substrate damage as well. So the answer is true. Cause of heat generation is because, see, we normally use e-beam evaporation for materials that has very high melting point, right? So electron, what happened to this? So electron beam actually generates a lot of thermal radiation. Okay, we are melting the material that has this melting point, say 1400, 1500 degrees Celsius, and that much of heat is required, like, for evaporation. In case of sputtering, it is different. We just hit the material and that will exist. So it is not, there will be some heating effect, but not that much. But in thermal evaporation or EVM evaporation, that is the main like process how we are doing the deposition. So there will be some thermal radiation towards the substrate as well, and that can damage some sensitive substrate. By sensitive substrate, it can be like flexible substrate, some kind of polymeric substrate. It Those substrate that cannot sustain very high temperature, like that is one trade-off. Like, if you want a very flexible substrate, that will not sustain very high temperature, because those are mainly polymer. So you cannot use it. Can create some stress, some deformation if you are using some flexible substrate. And another thing is that, as I mentioned earlier, see, you have already some photoresist pattern on top of your substrate, and again, photoresist are polymer. And if you want to do deposition on top of it, and you will etch it, say, later, or do a process called lift off later, then your photoresist property will change, because with that heat, some kind of chemical reaction will happen. You will not be able to remove your photoresist as easily as possible. This is what we like observe it uh, when we tried, like, e-beam evaporation on a, like, patterned wafer. When the pattern was done using for some photoresist, the photoresist became so hard that it was so difficult to remove. Okay, so this cross-linking kind of problem happened. So I'll write down the reason. E-beam evaporation generates significant thermal radiation. Can affect the substrate. Stress or deformation. Next, can cause unwanted chemical reaction at high temperature. So some kind of substrate cooling can be used along with this kind of system so that the effect is less. Okay, let's go to the next question. So this I explained in sputtering. So in magnetron sputtering, the presence of magnetic field helps in bash. So the answers options are: it increases deposition rate, option B is reduces the ion bombardment, option C is hits the target material. So what is the correct answer, and you can give me the explanation as well. Option A, that is it increases the deposition rate. And how it increases the deposition rate, you can briefly explain the reason as well. Okay, so I will write down the answer. Yes, you are right. In magnetron sputtering, the magnetic field actually increases the deposition rate. So that is the correct answer. So what happens in magnetron sputtering? You have this target, you will bias it, and your substrate will be at the top. So this is your substrate or substrate holder. This is your target. There will be like magnets here, small magnets here. It will be like alternate north south, and these are arranged in a particular arrangement. Okay, so what happens, your plasma will be created here. So there will be argon plus electron minus ion. So this argon plus ion and electrons, so this plasma will be trapped near this target. The reason is, so you know, these are like magnetic fields because of this magnets here. And we discussed earlier that electrons and like ions basically will be affected by the magnetic fields or electromagnetic wave, right? So we already know this, like if there is a current carrying conductor, there will be magnetic field around, and magnetic field actually changes the current and all these things, right? So because of these magnets, your plasma or your ions will be trapped near this target. So the sputtering ions will actually hit the target again and again, and your deposition rate will be faster because it's not like one bombardment, it's like multiple bombardment due to this presence of this magnet um, with the same argon ions. Okay, so that actually increases the deposition rate. So the magnetic field trap the ions close to the target, which enhances plasma density and increases the number of ion bombardment. This increases the sputtering deposition rate. This is compared to a traditional sputtering system like DC or RS sputtering. I hope the reason is clear why magnetron sputtering is preferred over conventional like traditional sputtering system. So let's go to the next question. During a PVD process, PVD is physical vapor deposition, a quartz crystal microbalance QCM is used to monitor the deposition rate. How does it work? I have explained briefly. You can write down whatever you understood. Okay, I'm giving you some more time. This is not an MCQ question. The question is how a quartz crystal microbalance works, like how it monitors the deposition rate or the film thickness. depends on the piezoelectric resonance frequency change. Yes, because due to deposition the mass will change and the mass will affect the resonance frequency. So I have explained earlier, like in a quartz crystal microvalence, there will be a like crystal that vibrates at a certain resonance frequency when an AC voltage is applied. Okay, this is due to piezoelectric effect. It has certain resonance frequency. Now, based on the weight, so how the weight will change on the crystal, because with deposition, some part of atom will get deposit on the quartz crystal monitor as well. Okay, some deposition, some atoms will deposit on the monitor and the crystal, and the mass will change, and based on that the resonance frequency will change. So there is some calculation like how much the resonance frequency change, that will actually tell what is the thickness of the film. Okay, it gives the deposition rate, also the film thickness, like at the end what is the thickness of the film. Okay, so this is connected to a display unit that will give you all this information. So the answer is, I will write down the QCM consists of a quartz crystal with electrodes when AC voltage is applied. The crystal vibrates at its resonance frequency. And this is due to piezoelectric effect. As material gets deposited, its mass increases, causing a shift in resonance frequency. The chains can be correlated to the thickness of the film deposited. So this is I have given you the explanation just for your reference, and let's go to the next question. So this is okay, so I've already discussed this. Let's just keep it. This is question 6. So what are the key components of an oxygen plasma system? So you have watched the lab video, so you can tell me the answer. What are the key components of an oxygen plasma system?
Ma'am, vacuum chamber,
Hmm.
then uh, one supply was there, gas supply, I think.
Oxygen cylinder, yes, because we will create oxygen plasma, so we need a oxygen cylinder and connection to the system.
Yes, and they were controlling something with that nodes. Some RF controlling system was there.
RF power, because to create plasma we need some power and we use RF energy for that. Yeah. So there is a RF generator, and then there is this coil, and then RF signal generator, and the coil will actually transfer the energy to the oxygen, and that will create the plasma. Okay. And of course we have the main chamber to create plasma. So these are the components, so I'll write it down. So first is RF power source. So this is to ionize oxygen gas. Okay. Next is a plasma chamber or the main chamber where you will keep your substrate. Is where the plasma is generated. Next you will have a vacuum pump. Why? This is to maintain a low pressure. For plasma formation. Now why we maintain a low pressure? So it to create plasma we need a low pressure environment, that is for stable ionization of our oxygen gas or whatever gas we are using. In case of oxygen plasma system will use oxygen gas, and that the stable plasma is required to get the effective surface treatment whatever we are aiming for, whether we are cleaning the substrate or using it for surface activation or bonding. Okay. Low pressure environment. Ensure stable ionization of oxygen. Also, if the pressure is high, then there will be again a contamination on our wafer itself. Okay. And the next is oxygen cylinder. So these are the key components of oxygen plasma system. It's a very like small and simple system, but used in various application inside a fabrication line. Okay. Okay. Have some time. We can take one more question. Arrange the following steps in the correct order for oxygen plasma system. 1. Apply RF power. Introduce oxygen gas to the chamber. 3. Generate plasma. 4. Place PDMS inside the chamber. 5. Activate PDMS surface. For bonding. 6. Evacuate the chamber using a vacuum pump. You can tell the correct order, like 1, 2, 3, 4, whatever the correct order. Get answer. You have the answer. 462, and then 1. We'll apply RF power. Then we generate plasma and then activate 1, 3, 5. Yeah. So the answer is, first we will place our PDMS inside PDMS or any other wafer, whatever we are trying to do. Then we will evacuate the chamber using a pump to create low pressure environment. Then we will introduce oxygen gas and then apply RF power. We will tune the RF power so that we get a very stable plasma. Okay, that will create plasma, and then after a treatment for certain amount of time, we will that will activate the PDMS surface for bonding. We'll stop the process and then we'll take out the PDMS substrate out and we'll do the bonding, okay, immediately after that. Okay, I think we don't have much time, so these are the questions I have for today. Like, I have few but don't have much time. So if you have any question you can ask, otherwise I will stop the session here. Okay, no question. Then thank you for attending the session. I hope it was useful. So I will upload the slides and videos. So if you want to need some clarification, you can watch again. And see you in the next session. Thank you.